Okay, good afternoon, everyone. All right, good afternoon, everyone. Today we're very happy to have Yael from Princeton University. Yael is a professor of neuroscience and psychology from Princeton University and the co-founder and co-director of the Radcliffe Princeton Center for Computational and Cognitive Neuropsychiatry. Her lab studies the computational processes underlying reinforcement learning, focusing on how attention, memory, and learning interact to construct task representation. In addition, she applies ideas from reinforcement learning to understand and treat mental disease. She won several awards, including Presidential Early Career Awards, but the proudest career accomplishment is winning a Graduate Mentoring Award. And today we're going to hear about latent cause inference and mental health. Thank you for coming.
Hi everybody, can you hear me okay in the back? Okay. Hope I won't fall off this stage, it's so small. Has anybody fallen off before? Okay, I hope I won't be the first. So when you look at this image, you probably immediately infer that we took this picture in the height of the COVID pandemic. So that's an example of latent cause inference. There is a cause that is hidden to the observable that you see, and you immediately make that inference. And in fact, we make this kind of inference all the time in our life. So for instance, when you decided whether to come to listen to this talk, you had to make some inference about whether this talk is worth your time. So you might have used all kinds of information to make that inference. For instance, maybe you've already heard me speak and you know that you like my talks, for instance, or maybe you know what my lab is working on, you've read our papers, or you know something about the topic of latent cause inference, or you're interested in mental health. Or something more general, you know about this seminar series and you know the quality of talks that are brought here. All of these together help you infer whether this talk is worth your time. So that's one thing that you can do with latent causes. You can decide on your actions based on them, but the other thing that you can do is apply apply learning to these latent causes. So for instance, if you leave this talk thinking this was a good talk, there's no point learning specifically about this talk because it's never going to happen again, like this exact one. It's done. What you want to learn is something more general about the topic, about the speaker, about these seminars, etc. So what I'm trying to say is that latent causes are a way to group experiences and generalize across them, both in learning and decision making. And this comes from realizing that no two events are ever exactly alike. So all of learning is really generalizing from something different. And what we want to do is figure out how widely we can generalize. The wider we can generalize, the more experience we have to build on, but we don't want to put in things that are irrelevant and incorrect. So the real problem of learning is where to put the boundaries on how much we want to generalize. Okay, so my lab has been studying latent cause inference for 15 years or so. It makes me feel really old. Don't want to think about people here who were my teachers. Sorry. Yeah, this is what happens when you come back home. And what we found is that latent cause inference, as I described it now, it seemed like a very fundamental thing, and we found that it's a very fundamental cognitive process. Really, when you think about how we deal with any bit of incoming information, the first thing that we have to do is decide of what kind is it, and that's latent cause inference. So we've shown that perceptual similarity is very helpful in this kind of inference, and so it helps us determine what to generalize across. We've shown that latent cause inference influences memory organization and memory retrieval, that prediction errors lead to inference of new latent causes, and that explains things like why extinction paradigms don't actually erase the old associations, but rather start a new association. We have work, and I talked today in previous meetings about this, work suggesting that latent causes are represented in the orbitofrontal cortex. And we even have ventured all the way to social decision making and shown that social evaluations can be skewed because of latent cause inference. So this is all already published work, and I'm not going to tell you about it today. One, you can read about it, and two, I've given talks here before in different forums, and even in this forum, so you might have heard about all of this. Instead, what I decided to do today is share results of several recent studies that are not at all, nothing is published yet. I think not even a preprint. No, one of them has a preprint. And I'm going to talk about two major lines of work. One is looking at transdiagnostic relationship between latent cause inference and mental health, and the other is looking at latent cause inference and relapse after successful psychotherapy. And as I was thinking about this, meeting with people this morning, I thought maybe I need to give a word or two about why I moved to mental health, because I wasn't always interested in mental health, and I think many of you are doing very basic science and might not be thinking about mental health all the time. I totally was there too. So I just wanted to say that, I mean, apart from the fact that mental health is interesting on its own right, if you think about mental health in the brain, I think mental health problems, symptoms, issues, really sit at the connection, the dynamic interactions between different cognitive functions. So it's a really complex but interesting space to look at, and that's one of the draws for me there. Okay, and of course asking questions during. So I know you're Israeli, it's okay. So let's start. So the main question that we're starting with is this fundamental process I just talked about of latent cause inference related to mental health? And or how is it related to mental health? And we had specific hypotheses, which I'll get to in a bit. But when we wanted to do this, we were interested in individual differences in latent cause inference. So we know a lot about the process in general, but differences between different people might be related to different mental health symptoms. So we were really racking our brain on how to measure this, and I want to highlight Sarah Dubrow here, who tragically passed away from a very aggressive cancer 2.5 years ago. But this is basically her work, her brainchild. We sat for weeks and months, and I dare say more than a year, trying to think, how do we measure latent cause inference properly in humans in order to measure individual differences. And in the end, we came up with a maybe straightforward solution that, scientists don't always think directly at the right solution, which is let's just break our stuff. Let's just ask them directly. Yeah. So this has never happened, actually. Yeah. Thank you. So let's just ask people directly what the latent cause is to a specific stimulus. So we designed a task that looked like this. This was pre-COVID, I promise you. We were at premonition, I guess. So the stimuli were these, we called them microbes. We told people, you are a microbiologist. You've taken photos of different microbes at different locations. Each location has its own strain of microbes. Microbe strains will have many or few spikes and long or short spikes. So there are two dimensions here that differentiate between strains. And then we lost all the labels of the photos. So what you're going to do is you're going to look at the photos and tell us what strain the microbe is from. So they're mostly kind of in order because you took them at different locations, but some also fell out of order. That was the weird cover story. So what they do is they look at a microbe and they tell us which strain it's from. At first there's only strain number 1. The first microbe is going to be strain number 1. And then once they choose a strain, another strain opens. So in this case, they've already had strain number 1 and 2. 3 is darkened because it's a new strain that they haven't inferred yet. But they can tell us that, okay, I think this is now strain number 3, and then they'll have number 4 available as well. So at any point in time, you can choose any of the previous strains or a new one, okay? And the structure of the task is this, and it's a busy slide, but I'll take you through it. Basically, what you see here on the x-axis is the number of spikes, so few or many, and on the y-axis is the length of the spikes, so short like here or longer like there. And what you see, and each, so this is trial number 1 is going to be a microbe with, this many spikes with this length. And you see here that this is trial number 1, 2, 3, 4. They're all very similar. So that's kind of one strain of microbes. And then on trial number 13, it goes to 14. So starting a new strain. So these are going to have many more spikes than those. And so the subject can realize that this is a new strain and say this is strain number 2. And then we hang out in this strain for a while, so 15, 16, 17, 18. And at some point we'll go to the next strain and the next strain, but there are also some jumps back. So from 24, you go to 25, and then 26, 27, and back to 28. So these are the ones that fell out of order. So basically we have trials that are a new strain, trials that are a revisit to an old strain, and the rest of the time you're just hanging out in the same strain, the same latent cause. And so this is one block. They did a whole bunch of these blocks, actually 8 of these. They get no feedback. So we never tell them this is the correct strain or something like that. So there are always 4 in the ground truth, but they don't know that. They can infer 15, they can infer 81, or as many as the trials are. Not 81. 70 something. They can infer 1. Okay? Does that make sense? Okay. So how do we model this process? Because we're going to want to look at individual differences in the parameters of how people make these decisions. So we've been using for a long time to model latent cause inference. We've been using this model called Bayesian inference with an infinite capacity prior, which is a very long name for a pretty short model. It's also called the Chinese restaurant process prior, so maybe you've heard of it in that name, or an infinite mixture model. And this came from work from Sam Gershman, who was my first graduate student, one of my first graduate students. He's now faculty at Harvard. And the idea here is simple. The idea is that your prior belief about how the world works is that observations are caused by latent causes. I'm going to take a tiny aside here to say caused. I realized I meant to say it earlier and I forgot. So remember that I had, all the things that the latent causes for will this talk be good? So the seminar series was a latent cause, but of course it doesn't cause this talk like in a causal, physics causal way. So when we're talking about latent causes, we're really talking about groupings of things, not necessarily an actual cause of the observation. So I will sometimes say cause and cluster interchangeably because that's how I think of it. It's really just a cluster of things. So observations are caused or, by latent causes, and the prior belief is that all else equal a prolific latent cause. So a latent cause that's caused many previous events is more likely to cause the next event, the next observation, right? That just makes sense. Whatever happens a lot, so it has a higher probability. So the way to calculate this, the simple equation is the probability of the latent cause of trial t plus 1, the next trial being latent cause number k, is just proportional to nk, how many events k has already generated. This is true if k is an old cause, but we have an infinite capacity prior. We don't know how many latent causes there are. We want to always have a possibility of making the new latent cause, or inferring the new latent cause. The new latent cause, its n is going to be 0. So instead of 0, we put alpha there. So the number of possible latent causes is unbounded. There is some small probability of a new latent cause on every trial, right? This is the prior. And in Bayesian inference, you take the prior belief, and then you see the event, and you calculate the likelihood of that event, and you multiply the prior by the likelihood to get the posterior probability of the latent cause. So the likelihood is really simple, too. It depends on the domain of interest, but the idea is that each latent cause tends to produce similar trials. Like what I said about the microbes of the same strain kind of look similar. So in our case, we just had a Gaussian on with some mean for the number of spikes and some variance, and some mean for the length of spikes and variance. But you can put whatever distribution works for your domain. So this is the standard model for latent cause inference. For those of you who know this model, or maybe some of you are really strong mathematicians, and you immediately look at this and you say there's nothing here about order. So this is just about the number of previous trials, but it doesn't say what happened recently versus happened a long time ago. And in the real world, order matters. Time. Things usually persist for a while, and also that's what we had in our task for a reason, because we were trying to model the real world. And so we used not this, but an updated model from Lloyd and Leslie, and this is work of Sashank Pisupati, who was a postdoc in my lab, and now works in Limbic in London. And this is called a persistent Chinese restaurant process prior. So the addition here is that we say with some probability we stay in the same latent cause that we were in the last trial, and 1 minus that, you do the whole Chinese restaurant process. So this means that in our model we have 3 parameters. We have the probability of staying, we have the probability of a new latent cause, and we have the parameter, the Gaussian, the variance of the likelihood. So, computer. So the parameters that I just talked about are the new cluster parameter, the persistence parameter, and the variance parameters, the 2 variances of the 2 cluster of the 2. The Gaussian is 2-dimensional. In each dimension we have a variance. Behaviorally, we have direct measures of these, right? So we can measure how many clusters a person inferred. They literally told us how many times they revisited rather than started a new cluster, because a revisit involves a big perceptual change. So you can either go back, or you can say this is a completely new cluster. So these 2 kind of trade off in some sense. And then we know the cluster size because we just know what they put in each cluster. So we measure these for each subject, and just to make sure that this is a useful task for looking at individual differences, we have to know that the task is that the task has good psychometric properties. So I want to show you here really quickly that the model parameters are recoverable. So if I generate data from this model with settings of these, with specific settings of these 3 parameters, and then I infer the parameters from the behavioral data, you see that these basically lie on the identity line. So it's easy to get back the parameters that generated the data if this is the correct model. And also empirically, so this was all simulations, but but empirically in our data, we had 8 blocks over 2 days. So we can estimate the parameters for each subject from only the even blocks, and then and separately from the odd blocks, and you see that they are highly correlated as well, or from day 1 and day 2, and they are highly correlated. I mean, they're not as highly correlated as these, but it seems like these measures are not just, the variability here is not just noise. It really is telling us something about some stable individual differences. Okay.
The data here was generated in the sticky changes process as well.
Here, this is human data.
I understand, but the data they took the task on was generated by this process?
No, the data was literally what I showed you, which is not generated by the sticky process. No, the sticky process will generate more clusters than we had. We had those 4 specifically. Yeah. Okay. So now going to mental health. So in our hypotheses. So the question on our mind was, if latent cause inference is such a fundamental process affecting so many cognitive processes, then maybe extreme values of these parameters would be associated with some mental health concerns. And we had specific hypotheses. One was, we thought that overgeneralization, making clusters that are too big, learning from one experience to something that's very, very different from it, might be related to things like, to conditions like anxiety or post-traumatic stress disorder. And this came from the intuition that with post-traumatic stress disorder, for instance, you can have one very negative event, and then it generalizes to many, many things that are neutral in your daily life. And so it seemed like a problem of overgeneralization. It was just this kind of like basic intuition, not based on data. And then on the other hand, we thought that undergeneralization might be somehow related to schizophrenia, because schizophrenia, literally the meaning, I think, is something like shattered world or shattered mind. And the idea is that there's phenomenological evidence that people feel that there is no connection between things and everything is shattered. And so we thought if you have 2 small latent causes, many small latent causes, you can't connect the dots basically between your experiences. So these were, we had, actually in the grant that we wrote, we had a whole list of hypotheses, but these were the ones that I was really willing to bet money on. And I'm telling you these, not because they turned out to be true, already spoiling, but just kind of, full disclosure, these were my hypotheses, turned out to be incorrect. All those papers where it always seems like the hypotheses, how did they know exactly what would happen? It's because the reviewers told them you can't write hypotheses that didn't happen at the end. Don't be that reviewer. These were our actual hypotheses, it didn't happen. Okay, so what did happen? So, in order to figure out the relationship between mental health and this task, apart from doing this task in a separate session, we asked people to fill out a whole bunch of questionnaires. So this is self-report of symptoms. This is all done online. I don't know these people and I don't know what their medical diagnosis is of any sort, but we've asked them tens of questions. I can't remember how many questions this all is, maybe 120 or something of the sort, on these different pre-validated questionnaires that we just took from the literature. We didn't make them up. So autism, depressive attributions, intolerance of uncertainty, mania, compulsivity, schizotypy, all of it. They just answer all of these questionnaires. And then, so we have for each person their answer on all of these questions. And what we did here is we took a page out of the book of Claire Gillen and Nathaniel Doss. So they pioneered this transdiagnostic dimensional approach of looking at what are the general factors in these data and do they correlate with the task. So we did factor analysis. So this is factor analysis just on the answers to the questions. And the top 4 factors that we found are plotted here. So for each factor, you see it's the weights, the loading on each of the questions in each of the questionnaires, and they're colored by the questionnaire color. And we gave them a name just, looking at the loadings and see, for instance, that factor 1 loads strongly on depressive attributions, on intolerance of uncertainty, and on anxiety, depression. A little bit also a social anxiety, etc. So we call that anxious depression, loads on the depression and anxiety questionnaires. Factor 2 is a factor that loads, so schizotypy is purple here, that loads most on schizotypy. Remember, we were interested in schizophrenia, so we're looking at that. We were happy that that came out as strongly. And this factor also loaded on some anxiety and depression and on mania. So we're calling that schizotypy, mania, and disinhibition, I think, came from here. Yeah, disinhibition. And then we have a factor of obsessive compulsivity that mostly loaded on compulsivity and intolerance of uncertainty that's known to go with that, etc. And the last one is positive affectivity and overgeneralization. So that came from a questionnaire of positive overgeneralization that really loads strongly here. And well, there's a little bit of mania here as well. So these are our factors. And now what we're going to ask, so for each person, we have their values on these 4 factors, and we have their parameters from the model, and we're just going to ask how are these correlated, if at all. And so this is the result. And the story to tell here, I mean, these are 0.05, the little stars, but the few stars, but these are the really significant ones that we've seen kind of withstand adding more data and things of the sort. And what we're seeing here is that the second factor, the schizotypy factor, loads on or is correlated with larger variance of the clusters. So when you look at these people who have high ratings on schizotypy, mania, disinhibition, and you look at the clusters that they look something like this. They're like large clusters that overlap. And so sometimes they jump between them, but it's not even clear. I mean, they literally overlap, so it's not really clear what's going on there. And thinking back, so if you think back to my hypothesis was that schizotypy would be 2 small clusters. Turns out it's 2 big clusters. Actually, I think, had I read the literature a little bit more, I would have realized that this is what we should have expected, because when you ask people with high schizotypy or people with schizophrenia to do regular categorization tasks, like you give them cards with different images and you say, just put these into categories, they do that. They make weird categories where, like, most of the animals are here, but some of the animals are with the fruit, and some of the fruit are with the vehicles, and just their categories have this kind of overlap, and that's what we see in the task here. Our other big hypothesis was about anxiety and depression, and here we don't find anything. I wouldn't really read into this, but I also want to say that this task is not really optimal for that, and this whole factor analysis is not optimal for that, because that factor 1 is kind of the factor that takes, I'm trying to go back to it, yes, no? Yeah. It loads on a lot. The first factor takes up a lot of the science, just like high symptomology, and this is not probably the best statistical way to pull out exactly anxiety and depression. I saw a question, yes?
Yeah. Did you have to somehow tune the signal to noise or the size of the clusters relative to their distance to get the separation, or?
You're asking about the initial task. So the task, the X and Y axis that I had there were perceptually, we did norming, so the distances between every 2 kind of places on that axis, they're not all the same, they're perceptually the same. So sometimes you have to, when you add the number of spikes basically is not linear on that axis.
No, but the statistics that you draw out, how do you draw up the examples? Because you have a cluster here, so it's some Gaussian.
Yeah, no, we didn't draw it as a Gaussian. We literally, it's literally what I showed you. So let me go back to it. It's literally this, but what I'm saying is that these notches here the differences are perceptually equal differences in perception. So it's like, Weber or...
But how do you sample the samples themselves? Is it fixed for all?
Yeah, it's fixed for everybody. Yeah. So our second block will be, they will all be moved a little bit, so they never see exactly the same stimulus again. And it's always clockwise, but it can start from here. Anti-clockwise. It can start from here and go like that. That will be another block and another block. So we have.
But the exactly same order.
It's always. It's always counterclockwise, these move a little bit and the starting point moves a little bit, but that's how it is. We didn't draw it in any, like we designed it. This was designed initially for an fMRI task, which we are scanning the task now, and there it's way more controlled. So when you jump to a new cluster, before that you have a jump of the same perceptual size within cluster. It was very, very controlled in order to be able to look at which areas of the brain are active specifically for generating a new cluster, controlling for the perceptual differences. So it started from that, and that's why it was like very regimented. And then for this individual difference, we just like dropped some of the controls, but we didn't change the task more than that. Yeah.
I wonder how one can control the differences in motivation.
Always an issue.
I don't care much about this task and clustering.
Always an issue, yeah. So we drop a lot of subjects because we do this online. So the number of subjects that we have in our analysis are a lot less than the number of subjects that we ran. One big problem is not just dropping them because they don't care about the task. If they don't care about the questionnaires, which are really boring, then that's a big problem. Because when people are answering the questionnaires randomly, it looks like they have high symptoms. And then they do the task randomly, and it looks like they can't do clustering. And then you can say, oh, people with high symptoms can't do proper clustering. So we're very, very careful with that. We have all kinds of attention checks during the questionnaires and during the task, and we ruthlessly drop anybody who we think is not paying attention. Yeah, we can't force them to pay attention. They're at home.
So all these participants were healthy participants or diagnosed?
These were just random participants online. They're not necessarily diagnosed. They're paid nicely for their time, but that's all
So it means you can run the questionnaire on a group of people and you can easily find some mental health problems.
Yes. There's a lot of mental health problems out there. Lots of social anxiety of people out online. Sorry?
Well, it look more like traits rather than clinical problem.
I'm not.
You are far away from clinical diagnosis.
Absolutely. When you said mental health disease, I thought, did I write that? Because I don't call it disease anymore. It just, it's mental health conditions or, concerns or, Okay. So we have this result, and it's again, it gives us some inkling. We're replicating all of this because there was a lot of, just because everything needs to be replicated as well. So hopefully this will replicate. But this gives us the schizotypy side. It doesn't really give us the anxiety side. And really what we wanted to, we were worried that maybe this task, is the latent cause inference that's done in this very, very laboratory artificial task, is this at all related to latent cause inference in real life? And so what we did here is we thought about kind of where do we find latent cause inference in real life? Well, everywhere, but one of the paradigms that looks specifically at how we chunk different things is a paradigm of event segmentation. So this is work of Oded Bain, who is also a postdoc in my lab and just started as an independent faculty at Weill Cornell Medical School, literally last month. And what he did is he comes from memory literature. He tested subjects, some of them the same subjects that did the microbes task, on tasks where we can look at naturalistic segmentation. Or segmentation to different chunks. So one of them is a story reading task, and I'll tell you more about it in a second, but this task has very well-controlled stimuli, and it's not prone to task instruction bias because we're not instructing people at all. We're just telling them read the story and click when you want to get to the next sentence. The other task is a movie segmentation task where they watch a movie and they're actually telling us when events start and end. So here the stimuli are kind of real-life, complex, audio-visual, and there's very rich segmentation behavior. So let's start with the stories task. So people are reading this story. For instance, you can read it now. Sentence after sentence. So there's one sentence on the screen. Juan had plans to catch up with Ryan. They press enter, and they went for a drink. They press enter. Juan paid for his ticket to the movies. Press enter, etc. So they're reading stories in this way. And we created stories where some of the stories have a boundary in the middle and some don't. So here when you read this one, you might have thought, what does that have to do what happened previously. So it starts kind of a new event, and it is an event boundary. And it turns out that people take longer to read a sentence like that. Like they might go back and read it again or something like that, or think about it some more. Their reaction times are slower. And we had an identical story that would have this same, well, not identical story, a story that would have this same sentence where this sentence was not an event boundary. So it's not an issue of how long it takes you to read the words. We can compare how long it takes you to read this when it's a boundary versus not a boundary. And so the slower you are, so in general we saw that people are slower on boundaries, but we're looking at who's more slower versus less slow, and how does that relate to mental health. So that's, I'm going to show you, let me just show you the results of that, and then we'll go to the movie task. Did I forget to say something here? Not really. Okay, so the main result, and here these are the same questionnaires that we ran before, but I'm not using the factors here. We correlated with the questionnaires separately, and what we found in all the different questionnaires, the one thing that correlated with slowness at boundaries was anxiety. So people who had higher symptoms of anxiety were also exceptionally slower when it was a boundary versus a not boundary. Everybody was slower, but they were like more slower. And that is...
Everyone was slower?
Everybody's slower for boundaries than for not boundaries. You have a big main effect, but then if you're looking at individual differences, the more anxiety you have, the more slower you are in the boundary versus non-boundary. And this is true if you look, this is separately significant if you look at a subscale of anxiety that's about avoidance and fear versus a subscale of anxiety that's more cognitive worry. So it seems kind of like a general thing. And so looking at this was interesting. Odette's first thought was that that people with anxiety are impaired in their boundary processing. And my first thought was that they're actually extra sensitive to boundaries, and that's why it's taking them longer. So to understand, to look at the difference between that, it's useful that we have another task, which is the movies task. So here people are watching segments of movies, Home Alone, and movies that you've seen. They watch clips that are short, 2.5 minutes, and in every clip they click whenever they think that one meaningful unit has ended and another has begun. And we ask them to do it twice on different days. First, we ask them to do the largest meaningful units that they can think of there, and the second time, so that's coarse segmentation, and the second time it's fine segmentation. Tell us every small change that whenever you think an event has started again. So, oops, I had that. So largest meaningful unit and smallest meaningful units, and that the second one was about a week later, so that they wouldn't necessarily remember exactly what they said previously and wouldn't be committed to it. And so, in general, this has been used a million times, this task, and people tend to agree on when boundaries occur. This is, events are events. So we can take, and others have done this, they take agreement as a measure of segmentation precision. So you can see where the whole group put their boundaries, and then I can take individual person, Eli, and ask how well do his boundaries agree with the group, and the more he agrees with the group, the more precise his segmentation is. And here what we see is that people with a higher anxiety score are more precise in their segmentation. So it's not that they're less sensitive to boundaries, they're very sensitive, at least in this task, they're doing the boundaries exactly right. And they were slower, right? Yes?
Between people with kind of anxiety, or
This is also online, same kind of thing with questionnaires. I don't know if they have a diagnosis of anxiety.
What it meant is, if you have, let's say you have two populations, right? It's easier. There's a question of how much agreement there would be with the average over the whole population.
Oh, this is with the whole group.
This is with the whole group.
Yeah.
Also maybe influenced by the number of people with anxiety or not.
This is a very continuous measure. We don't have groups of people. We don't have people with anxiety and people without anxiety. We have their questionnaires. It's a continuous thing. So we didn't divided into groups, but we can test that too. But overall, we have so many subjects, 461. The group average is very precise, and I think even if you took half of the people or a third of the people, it would look the same. So it's really an individual versus everybody else.
Do they believe there is a right and wrong answer?
No, there's no feedback here either. You watch a movie and you just...
No, but do they think either?
We tell them, tell us whenever an event
Just be more
ended.
cautious about...
Yeah, no, people with anxiety might be more cautious about everything, right? Yeah, I mean, we gave them instructions, so that's all. And here, just to give the full picture, this is only true for the social anxiety subscale, not the cognitive, not the worry subscale, but more the avoidance, fear, hypervigilance kind of, I'm aware of everything all the time. Like it makes sense, kind of the story of like everything in my life. I have to make sure when something ended, something else started, so I don't like misconstrue whether I'm in a dangerous or unsafe situation. Okay. And this is, I should say that all of these results are controlling for age, gender, cognitive abilities. So we had separate measurements of working memory and reasoning and verbal abilities. And we did a lot of other controls. This is like controlling for everything that we could. And the very last thing that I want to tell you here is, the next to very last thing, one more thing is that if you look at agreement between people's coarse and fine segmentation. So how hierarchical are they? Then people with higher social anxiety are also have better kind of hierarchy between their fine and coarse alignment. So they're really precise in this. So overall, they are better at event segmentation. And the last thing that I wanted to show, now this is correlating between the two different tasks because these 452 subjects did both tasks. The other results, by the way, we have also from another group, and it's replicated and everything. People who had this higher, were more precise in their segmentation, also had lower variance in their clusters in the microbes. So exactly the opposite of my hypothesis. I thought anxiety would be overgeneralization. Turns out that anxiety is very precise, small, pretty clusters, and good segmentation in the real world too. Slow, but good. Versus schizotypy that was this like complete mess in understanding the structure of what's going on here. Okay. And by the way, people with high schizotypy were worse at, so here on the right here are people with high schizotypy. They have a smaller agreement with the segmentation norm, and both in coarse and in fine and worse hierarchical. They're just, again, here it's a mess too. They're not very good at this task either. Okay.
Is there also any correlation with the number of boundaries that they put? Because
so interestingly,
could be more or fewer.
Yeah. So no, they put the same number of boundaries on average, just in weird places. Yeah. Also made the same number of clusters. It was very interesting. We thought we would just find big differences in the number of clusters. No, it's where you put the boundaries. Yeah.
Are you only trying to find correlates, or you try to insinuate something about the causal?
Wait, we just started. This is not even published yet. Yeah, no. In the end, we would want to figure out a causal mechanism, and that's what I'm going to show you in the second part.
Because that seems to the switch of the reverse hypothesis, because you assume that what would cause anxiety instead of defining anxiety.
Yeah. I will get to it, and I see that the time is 2:44, so I will quickly jump to the next part. So, interim conclusions. So, what I've shown you is that alterations in latent cause inference might be related to mental health concerns. And here I showed examples on a spectrum from anxiety, which is small, precise latent causes, to schizophrenia, large, sloppy latent clusters. Latent causes. I don't think this is the whole story. This is really just the beginning. We're starting to tap this. Only first steps, we're doing fMRI, and we're doing replications, and we're doing other statistical analysis, etc. Yeah, we're doing the imaging. I'm not going to talk about any brain today, but we are looking at the brain. But really what I want to go to is the second part, which deals with this issue of causality. and dives even deeper into anxiety. But first, I jumped really quickly. Any other questions about the first part? I've instilled impatience in you too. Okay. So, event boundary. Put that other story aside for a second. Now, this is work by my postdoc Isabella Vervian, who's on the job market now, but she's mostly looking for jobs in Germany because that's where she's from, not here in Israel. And she she's a trained clinician, a clinical psychologist, and also has a PhD in computational neuroscience. Amazing person, super brilliant. And she's really interested in psychotherapy. And she came to my lab to study learning because of this idea that psychotherapy is fundamentally a learning process. So when someone comes to psychotherapy for some mental health concern, they want to change something in their life. What the psychotherapist wants to do is help them change maladaptive action patterns or thoughts or emotion patterns, and that is going to be through new learning. So we're experts in learning, so maybe we can understand something about how psychotherapy works, how it brings change, when does it fail, why does it fail, for whom would it help more or less, because we're interested in, we're experts in individual differences. So that's the main question, and I'm going to talk specifically about cognitive behavioral therapy. And so a couple of words about cognitive behavioral therapy for those of you who don't know much about it. I didn't know about it until about 5 years ago. So in general, if you think about our life, it seems like things in the world cause us to react in different ways. Sometimes these are maladaptive ways. We can yell at somebody, we can feel really bad, all kinds of reactions. But cognitive behavioral therapy comes from the premise that actually this model is incorrect. The thing that we need to put in the middle is the world causes some interpretation in my brain, and that then causes my reaction. And this, for us neuroscientists, is exactly like, duh, of course. It causes a representation in our brain, and that causes us to do things, right? The world itself cannot affect our actions directly without going through our brain representations. And this is really good news, because our interpretations, while it's maybe hard to change the world, we can work on changing our interpretations in order to have different reactions if our reactions are maladaptive. And so what CBT does, the C in CBT, the cognitive part, are cognitive interventions that try to change our interpretation, and the B is behavioral interventions that try to change our interpretation. And so, for example, imagine I have social anxiety. So I feel that people are judging my behavior all the time. They're laughing at me. They're whispering about how silly I am and what that thing that I said was so stupid. So I start to avoid social situations. I just don't want to be around people. So what CBT will do, the cognitive therapy part, will be trying to think cognitively, kind of model-based reinforcement learning, if you want, about, is my model of the world correct? Like, when I saw other people laughing, could they have been laughing at something else? Did someone else just tell a joke, for instance, and they weren't judging me at all? So I do reinterpretation. I put question marks where I had exclamation marks, and I really try to think, like, is this the only way to interpret the world? And there's, I'm simplifying. There's a lot of work that's done with patients to help them rethink their interpretations. And then the behavioral therapy is literally, it's like, it's model-free reinforcement learning. It's telling them, okay, let's plan a social situation that you normally avoid, but it's not too bad, and let's just do it. Like, go out, go to the supermarket, and ask the salesperson, where's the pasta? Even if you know where the pasta is. Just ask them, and see that it's not that bad, that they didn't start laughing at you and think, how do you not know where the pasta is? They just, they just give you the answer. So you do exposures to social situations to learn that they're not really as bad as you think. And literally, like, you can tell patients, I tell patients, you can't tell your amygdala not to be afraid. You have to show it. So this is training the amygdala. Okay. So we were interested in psychotherapy, and specifically psychotherapy for anxiety. And you can think of psychotherapy for anxiety as just like a laboratory task, fear conditioning, caused some fear association, caused anxiety, right? So in our task, we have fear conditioning where there are two stimuli, the moon and the candles. On every trial, you see either this one or this one. The moon is half the time, 50% probability. It's accompanied by an aversive outcome, which is a loud scream of a woman. This is all online too. We love online experiments. So we can't give them a shock or anything like that. They're sitting with earphones and they calibrated the volume, and once in a while we say something really quietly, and if they can't hear it, then we know that they're not listening, and we throw them out of experiment. We say, press the letter F now. So they're listening to this, and these screams are pretty awful. Okay, so they start being afraid of the moon. So this is that we've acquired anxiety from the moon stimulus. And now we have them fill in some questionnaires about their symptoms, etc., stuff that we like to do, and then we do extinction. So the extinction is basically mimicking the behavioral part of cognitive behavioral therapy. You go do the things that you're afraid of, and you see that they're not that bad. So you see the moon, and there's no scream. And you see it again, and there's no scream and no scream. And so there are no screams at all in this phase. They again see the two stimuli. So cognitive behavioral therapy really works, and especially it works for anxiety. But the problem is, for many people, sometimes as much as half the people, fear will relapse later again. So their anxiety will come back. And that's what we're interested in modeling and measuring. So after this whole thing, really can't get far from that, we give them a different task for 15 minutes, and then we bring them back for a spontaneous recovery test. So we show them the stimuli again, and we measure their fear. And we're looking to see whether their fear relapsed, like happens in the clinic. At the very end, we have another phase of this task, which is a relearning phase. That's for model fitting. It doesn't hopefully mimic real life. Okay, so this is our task. And one thing that I didn't tell you is how do we measure their fear? Because they're at home, we can't do skin conductance, we can't do pupillometry, we can just ask them. So we ask them every few trials, how likely do you think each image will be followed by a scream? And they just tell us. We've also done other things. We've measured how much they like these stimuli. We've measured their reaction times. And all these things correlate. This one is the cleanest, so we just use this. But it is very explicit. Okay. So what does behavior look like? What we see here, over all of the 204 subjects I'm showing you here, we have many more. We have 700 and something, but we first analyzed a small group, and we wanted to pre-register and all of that. So what you see here is in acquisition, they learn that there's a difference. So this is the CS minus, the candles. So they're less and less afraid of the candles, or less and less predict to scream for the candles. And they're about at 50% for the moon, which is correct. It is 50%. And then in extinction, they decrease their prediction for the moon, so they are extinguishing. And then you see here the spontaneous recovery of fear. So after the 15-minute other task, they come back and we just ask them. We say, calibrate the volume again, okay? How likely is it that this stimulus will be followed by scream and that this one? And they go back up again. And then, there are no screams there, so that's short-lived. So that's in general over those 200 people, but if you look more closely, there are lots of individual differences. And the main thing, so we're interested in this spontaneous recovery, the main thing is about 60% of the subjects show this spontaneous recovery, but not all of them. There's a large group, a quarter of the subjects that don't show, very minimal spontaneous recovery. And here I'm just dividing them based on their behavior there, just to show you the individual differences. And also in the clinic, we know that not everybody shows relapse, so we were happy with that. There are two other groups. There are people that show spontaneous recovery for both. So we kind of call them, they're afraid of everything, but it's more like they're restarting. Their fear here is like their fear here. They might think, okay, task is starting again. Who knows, sometimes there are reversals, sometimes whatever. I'm just gonna assume that both are gonna give me a scream. And their last group, very few people, but we think that they're important too, and we have more of them in the larger sample, are extreme generalizers. They never really separate between the CS plus and the CS minus. They do decrease their fear in extinction, They do show spontaneous recovery. In relearning here, they are differentiating them, so they're not paying attention, they're just generalizing. So, yes?
Do you have control with a positive rewarding?
No, only this task. Okay, so 5 more minutes. I'm going to show you the model of this and finish up. So you can already think of the model here because we've talked about latent causes. So the idea is, imagine you see the moon and you hear a scream. So you assume that there's some latent cause that causes moons and screams. I'm going to call this D for dangerous latent cause because this is like a bad thing. And now a trial comes in which there's a moon and no scream. So what do? There are 2 things that you can do. One thing that you can do is, look.
Run away.
Okay, I think maybe I need to take out the battery from this guy. Or just turn it off. I'm going to have to stand here. So one thing that you can do is you can say, okay, the probability of scream is not 100%, right? So you can change. So everything in this model is learnable. The strength of these associations is learnable. So you can change that probability and say, it's maybe 75, 50%, etc. Or you can learn a new latent cause. You can say, well, there are some moons that come with a scream, and there are some moons that don't come with a scream. And think about anxiety in real life. Think about someone who's afraid of dogs, right? You might learn that this dog is not scary. This is the ones that don't bark and bite. That doesn't mean that none of the dogs bark and bite. So I still have the dangerous latent cause. There are the dangerous ones, but there are the safe ones as well. And so someone who does this kind of separation in their learning, in their therapy, they're much more prone to relapse later because they still have this scary latent cause, right? So later I can meet a dog and be like, oh, this is one of the scary ones, even though my therapy was all about like petting this other dog and not being afraid of dogs anymore. Whereas these kinds of people who change the probability of the scream, they have nothing to relapse to. There's only one thing that they've learned, and that's what they know right now, that dogs are very unlikely to bite you. Okay, so what differentiates whether you're that kind of person or that kind of person? So in our model, one thing that determines that is what is your prior on the strength of these connections. Right? When you see something for the first time, you have to have some prior on what is it going to look like, what does the world look like? And in psychotherapy, and in general, in the world of mental health, there's this cognitive bias called black or white thinking. Like some people think that everything is extreme. So black or white thinking is this kind of thing where like either it causes screams all the time or it never causes screams. There's no shades of gray. So this kind of person will be more likely to generate a new latent cause because this one is the 100%, that one is the 0%. Whereas if you have more shades of gray in your model of the world, then you maybe are more susceptible to learning within that latent cause, and psychotherapy will work better for you. So we ran this model, and we tried to think, our first intuition was that this is, I realize I'm telling you about a lot of things that didn't work today. Our first intuition was that this would explain behavior in our task because the people with the splitting to 2 latent causes would relapse, but it didn't. So it fits well here, but it fits really badly here because there's nothing specific that happens in the break here. Whatever you believed at the end of extinction, you believe at the beginning of the next stage. So then we thought, okay, what happens in the break? And one thing that Isabel thought of is we tend to forget things. So maybe in the break what happens, or in general, all the time what happens is these counts of the latent causes, the ends, they're slowly decaying. And here, at the end, after extinction, because of the recency, extinction is much more, this latent cause is much stronger. But if everything is decaying and the latent, and also, we model the time that went by, then this latent cause might be able to come back to life. And so she modeled that, adding decay of latent causes, and that explained, but you see that there's not enough spontaneous recovery there. And so, scratch her head more and more, and she was thinking, okay, there's a lot of literature that suggests that people, while they're forgetting things, we selectively replay and remember things that are motivationally important. We don't want to forget them, right? Evolutionarily, we want to remember, for instance, something very aversive. So what if we have selective maintenance of the memories of the latent causes that are associated with a screen? So the more latent causes associated with a screen, the more it will be protected from forgetting. And when we model that, we get exactly a fit for the whole data curve. And I'm going to go really quickly through this because of the time, but just like you can't even see the difference. So in each of the groups, it explains all of the group differences here. This model can really explain all of our findings, all of the different subtypes of people here. And just before the take-home message, I just want to say we're doing this really ambitious, ginormous study of 1,500 people with depression with depression and symptoms, who are doing this task and 2 other tasks, and then undergoing cognitive behavioral therapy online. And we want to see whether these tasks can really predict who is going to relapse, who's going to improve better from the treatment. And there's a much bigger story there that this is all part of. So I'm out of time. So overall, what I've told you is that because no 2 experiences are alike, the key to learning is smart generalization. And latent cause inference is this computational process that allows us to organize information according to similarity. And because it's so fundamental to learning and decision making, alterations in this process can be related to mental illness. And I've shown you some results from psychotherapy. But I want to say in general that there are many determinants of this inference process. So we've talked a little bit about the priors and likelihood and this replay, offline reorganization. So it's a really rich area for a lot of future computational cognitive neuropsychiatry research. So in case you are looking for a postdoc in a year, email me if you're interested in this kind of thing, and you can see us all without our masks, and thank you.
Maybe this wasn't a past bit at the end, but it's possible.
I just want to say it is 3, so whoever needs to go, I will not be insulted. Yes.
So it is possible that people begin it during acquisition infer there are 2 latent causes, but there's another possibility that they create a latent cause with a probability, and then during extinction they create an additional latent cause and they revert to the original, right?
Yeah. So initially we thought that that's what, let me go to our original explanation for all of this for extinction, and this came from the first paper from Sam Gershman. Sam Gershman's latent cause paper was to explain renewal after extinction. And the idea there was that you have one latent cause in acquisition, and in extinction, you learn a new latent cause. But that model had 100% reinforcement in acquisition. This came from work with rodents where you give them a shock on every trial. And so our imagination was not, developed enough at that point to realize that would not work here. Like none of the subjects here, the people here who infer one latent cause are the extreme generalizers. They generalize all through. Their model is a 1 latent cause model. Everybody else, so all but 9 subjects, have 2 latent causes here in acquisition. Otherwise, you wouldn't be able to show these big differences in behavior. So then the question is, what happens if you already have 2 latent causes, and how do you continue with that?
Yeah, I meant specifically not you have 2 latent causes for the moon and for the candles, but I meant for the moon and...
No, we have 3 actually latent causes. We have 2 latent causes here. Sorry, you're right. We have 2 for the CS class. Yeah. So these people have 3 latent causes. I'll go to the one that I skipped over.
Actually, during extinction, do 4.
So they have these 3. So one that goes to the moon and a scream, one that goes to the moon, and one goes to the candles, with no screams here. And what the model is suggesting happens here is all of these decay over time, but this one is preferentially maintained, replayed, and that's why it comes back. So only this one comes back. You come back to that one. Yeah. I guess. Yeah. Whereas this group these were fit, these people, if you look at their, the parameters, so we fit the model individually to each subject. And here I'm just like grouping them by their behavior, but it was, the model didn't know about these groups. So these are people that the model ends up inferring selective maintenance for them, a high selective maintenance, whereas these, the model inferred no selective maintenance. And not everybody has this kind of replay. So everything decayed here, so there's no spontaneous recovery, and these people had such strong decay that they start a new latent cause here. And those people, like I said before, they have just one latent cause. So this is how the model explains all this, but I want to say one other thing. It turns out I just lied. If you look at these people, just pull them out and look at the parameters, for half of them, only half of them, the model predicts spontaneous recovery. And for the other half, it doesn't. So there are two mechanisms here. When you divide the people based on the model prediction, you see that they have, their whole learning curve is different. Like, we didn't know to divide them based on that to start with. But the people that the model predicts spontaneous recovery for, they also have higher prediction here. They're constantly overplaying the scary thing. And the people that don't have that, the model doesn't predict spontaneous recovery for, because that mechanism, like, the model is fit to all of these data, not just to this data point. So in order to explain all the rest, it has to like give up on explaining this. So there's another mechanism there that Isabel's working on now, and she already told me that there's a model now that can explain 80% of these subjects, not only 50%, but she's going to show it to me next week. Okay.
Ronnie Paz make a big story for different generalization for positive and negative.
Yeah.
So what is your point about it?
Exactly. It's the same idea that you might have selective kind of enhancement of anything that's associated with negative things, or with very highly motivational things. Maybe very, very positive things also have the selective enhancement. And this is one of the consequences of
But
that.
would it be only a scaling between the positive and the negative, or would it be two different processes? Namely, like Ronnie, you need to be highly generalized for negative, but you better don't generalize for positive.
Yeah, I mean, the way it comes out in the end, like behaviorally, it might look like scaling, but is it really that, or is it that you have one latent cause that you're much more likely to infer? And so when you're thinking about, so in Ronnie's experiments, he has a stimulus and then he tests stimuli that are a little bit different from that, right? So the stimulus, so the likelihood is lower, but what is the prior, right? And if the prior for this one is higher, it's going to make wider generalization because there's a higher prior for that. So I think you can explain the same thing. It's not really scaling, it's enhancing the prior. Yeah.
So these people really went to cognitive behavioral therapy, or it's like
These people are?
these people went to therapy and relapsed, or?
Oh, no. Again,
Okay.
just random people online.
So there are studies that says that self-reported measures like impulsivity, that doesn't correlate with the experimental task in the laboratory. There is recent study in Nature Neuroscience where they trained on many basic cognitive control tasks, but that doesn't go in the real world. Like, that doesn't influence the academic achievement and other stuff.
Yeah.
So maybe whatever you are inferring from here to psychotherapy, that's just a hypothesis.
That's the big question. That's why we're running that big study now on 1,500 people. And we're trying to test whether this task, whether spontaneous recovery in this task and parameters of this model will indeed predict actual relapse after psychotherapy. So they're getting psychotherapy, and then we're following them for a whole year, asking them every few weeks or every few months later on for their symptoms, and we're going to see. And it's, big question mark. It might not have any predictive power, but it might predict.
Isn't it like this spontaneous recovery previously done? And it's like basic memory.
Oh yeah, spontaneous recovery has been shown a million times.
So the relation between this result and psychotherapy is more.
Yeah.
I'm a bit confused about this figure. So I'm looking just at the acquisition phase. You have this like fine structure that you see.
Oh yeah, everybody saw the same exact sequence of events. So the trial with a screen, the trial, like, we want to look at individual differences, so we want to make the task be exactly the same for everybody, so there are no task differences. And that's why it looks specifically like that. Yeah?
I might have missed it, but is there a difference between the spontaneous recovery and the no recovery and how aversive they experienced the aversive stimuli before in the
Oh, that's a good question. We have those data. I'm not sure we tested that. Not sure we tested that. I wouldn't be surprised if there's a difference, but I'm not sure we tested that. Yeah, it's a good question.
And even if, suppose if you establish a link between this task and psychotherapy, actual treatment, how it is?
Okay, so the big study, the reason what we want to predict, the big study was not only about this task, it was really about model-based and model-free reinforcement learning, and the idea that in cognitive behavioral therapy is model-based, and behavioral therapy is model-free. And so we can measure individual differences in how well, for instance, do you translate cognitive learning to behavioral, model-based to model-free. Because patients will often say, I understand exactly what you say, but in the moment, I can't act on it. Like I don't feel it. I understand it, but I don't feel it. So one of our tasks is measuring that translation. And we're predicting that people who are bad at that translation won't benefit from the cognitive therapy, at least early on. And people don't stay in therapy if it doesn't work. So we want to give them the thing that will benefit them early. So we're trying to predict who will benefit from cognitive. For the behavioral and the relapse, there's this task and there's another task. So what we want to do is to be able to give and to aid psychotherapists in choosing what to start with, what will be most effective. And these are just two different treatments. There are many others. So Isabel has a long list of questions that she wants to study. But right now, there aren't many like specific aids to choose which kind of therapy to give a person. So yeah, that's the goal. Thank you so much. Thank you, Ken.
בעצם על הדיספליי, בעצם זה שם, בבחירה של איזה זיכרונות לעשות עם ריפליי, חוץ לעשות
אנחנו עשינו ריפליי בפרופורציה לעד כמה הסקרים היה associated עם כל latent cause. People with black and white thinking will have some latent causes with a lot of screens, so those will be replayed very strongly. So yes, those do interact. The people that have more, like less black and white thinking will have, yep. Yeah, that's a good point. I didn't think of that, and we see that in the clinic. People, these things come together.
Feed themselves.
Exactly. You get into some corner. Yeah.
ואז מגיעים לסוף שבעצם חצי.
טוב, אז אני אגיד לך, תודה רבה. וגם מה הייתה צריכה ללכת. ואת יודעת את הנושא שלך?
כן.
את מגיעה אחר כך אליי בשביל.
כן.
נכין לך קפה.
תודה, יש לי.
Hi, big fan of your work.
Thank you.
Latent state OFC stuff is very inspiring for our own work.
רק רציתי להגיד לך שלום, אני לא יכול להישאר, אבל
אני בארץ עד אוגוסט.
אולי יש לזה משהו.
קשר
whole idea.
סבבה.
So there's a crazy hypothesis that I'm trying to push in our work, that what the OFC is involved in is not exactly just latent state inference, because to do latent state inference, let's say you could have a memory, right? Any memory is latent, right? And you would imagine we can have memories even if we inactivate the OFC.
Absolutely. We know that. So right, like people have OFC lesions, they don't lose their memory.
Okay, I'm actually not aware of OFC lesions.
Lots of people have OFC lesions because whiplash kind of car accidents. We have a little bulge in our skull right above the OFC, so if you have like bad whiplash, it could damage your OFC.
Is it like the football injury? Is it the chronic? I forgot what it's called.
It's a lot of car accidents.
Mhm.
Yeah,
Okay.
lots of people.
So there's something special going on there that's involved in the latent state inference. That's not just imagining something that's not presently in front of you.
That's right.
So the claim I'm trying to push is that it's about so you showed likelihoods and you showed like, okay, there's, Gaussians and, maybe there's a covariance between the latent variables. So the likelihood could have, a covariance. And in that case, or more complicated cases, obviously, then what's happening, what would be important is the interaction between the latent variables. When you get an observation, right, that observation tells you a lot more information than just having the latent variables individually or separately.
Okay.
And so I'm just curious about
So
what
you're
your
thinking
thought.
the OFC is important for the relationship between latent causes?
Yeah, the interaction. So like, for example, when it's anything to do with behavior, right, then there's going to be the latent variable that's generating the stimuli and then something to do with the optimal action.
Well, one, good luck, because that's really hard to show, because you need a really complex task. But also I think you can see from animals that the effect of OFC lesions or inactivations, they have effects on really simple tasks where there isn't a complex relationship between latent causes. So it might be that, of course, whatever gets damaged is even more important when there are complex relationships, but it can't be only about the complex relationship. Because just reversal learning is the main the hallmark impairment of OFC lesions, and that's just like it's either this one or that one.
I would claim for like reversal learning, it's about the latent the latent generator of a stimulus, and then the latent variable that's optimal action, optimal behavior could be in the brain represented as like, okay, you have this some latent variable in the motor cortex and latent variable in sensory cortices, and even though in the task they're the same variable, with regards to the brain, the OFC saying, okay, motor cortex latent variable, auditory stimulus latent variable need to be connected. Is a claim.
You can always explain things in a more complex way than a simple explanation. But also, wouldn't that be true for any single task? Any task, like I'm drinking my coffee, I have to represent that there's coffee here, that I need to lift it, there are lots of this is not going to be prone to OFC lesions. I can drink my coffee totally fine without an OFC.
A basal ganglia stimulus response, you don't need, there's no, you don't really even need the cortex at that point. Like if you, so that's the claim I would make, is that like if you can do something with just like stimulus response, basal ganglia.
It's very similar to the claim that we made that, if you have one latent state, if you have only one state, then basal ganglia are enough because you respond to the stimulus. But if you need to interpret the stimulus within one of a bunch of latent causes, now you're in trouble and you need the OFC. So the question is, what does your story add to that? And I'm not saying that my story is right and yours is wrong. You're going to have to find the exact task that shows that you need that added thing.
What we're trying to show right now, and this is the huge we're in the lab disagreeing on it, is that
what lab are you in?
I'm in a duel with Ran Lotem and Jonathan Kadmon.
Okay, yeah.
And what they have a mouse task, and the mouse needs to do context-dependent integration.
Yes. So Jonathan told me all about that task. Okay.
So the claim
I was telling him this is just the latent causes. Yeah, exactly. Yeah. Okay.
So the question is, we inactivate the OFC and we see some kind of bump in the response, to some stimulus, even with some context-dependent bump to the response.
Yeah.
Now the question is this context-dependent impulse, or is it like a stimulus response, or is it just you have integration that has lost any context dependence, and based on reinforcement learning, you're just more or less likely to respond model-free?
Yeah. No, I talked to him about this task this morning, and I was wondering, I haven't sat and simulated it, if you have, what is the optimal solution if you have only one latent state there? If you can't separate between the safe and the dangerous states, you have only one state, what would be your optimal policy for behavior?
So it's hard. So we've looked at like saying, okay, you have state inference, but it's independent of context. We have context inference, and it's independent.
But you
of
can
state.
infer theta. But in my story,
Yeah.
you can still infer theta, the probability of noise or the rate of noise you can infer. You just don't know if you're in the safe state or in the dangerous state.
So I think that's model-free reinforcement learning, right? Because I'm not sure, but
and that's why I think it would generate the behavior that you're thinking.
so if you, well, the question is, so there's a few models we're playing around with. One is like, oh, if the mice are responding to the onset of the stimuli or the actual observation. So if you respond to the observations, you don't get a bump at all because it'll be like exponential decay. But if you respond to the onset of the stimuli, then you do get this bump. So that's the debate. Or one of the debates.
So yeah, I don't know all the details of this, but I can just say that a lot of research suggests that animals respond to onsets in general.
Yeah.
Even when they should respond to, even when there are other things that are more important, like duration, onset is really important. It is what it is.
Thank you so much.
You're welcome. I really like the talk. I have a really short question. What was the relearning for? Like the last start again part?
Yeah, we added it because we could. And then, when we first did it, and then it turned out that it does help the model. It does help the modeling constraints a little bit more. Because there's a question of, are you learning? So some people relearn faster and some people relearn slower. So it gives more information about whether they're learning new latent causes or they're applying their old latent causes. Okay. So those people who started from scratch, basically, their relearning is much slower. They're just starting from scratch. Like the people who are afraid of both stimuli after the extinction, they also relearn as if they're starting everything from scratch. So it
like
turned
more
out
evidence for how much.
It's just more things for the model to chew on and fitting. And also we're happy that we did that because we can see that the generalizers in the second time around, they do start separating. So we're like, okay, they're not paying attention. So serendipitously, it turned out helpful, but we just put it there because we could. Yeah.
Okay. Thanks.
Yeah, thank you. I was wondering if you look at like interoception at all in terms of like a lot of the like latent causes that you're inferring it to do with kind of like sounds or things that you're seeing, and I guess like I don't know, my work is a lot of interoception, so I'm interested in it. But in terms of like the way that you kind of perceive and infer signals originating from within your body, whether that's like your heart rate or like any level
that's super important. Super important. I'm glad you're studying it. We haven't done any work with that yet, but I think like from my clinical knowledge, I think all the internal stuff is just as important as the external stuff. We just, it's harder to measure it and control it, and so we study it less. But especially for inferring danger, like if my heart is beating fast, I infer that I'm in danger just because my heart is beating fast, not because of something that I've seen outside. And so all of that, like I think latent cause inference is really using a lot of bodily cues as well. I have lots of thoughts about this, but like no actual work on it.
Interesting. There's this paper that I was thinking of that's like also looking at fear learning and extinction and like recovery of the fear learning, where the stimuli, I think they were like short electric shocks, and they were either given like on systole or diastole, I don't know, I can never say, diastole, and it
of the heart.
Yeah, of the heart.
Oh, wow.
And it like when
it made a difference.
Yeah, when within the cardiac cycle the shock was presented during learning, made a difference on the fear recovery mechanism.
Wow.
Which is super interesting.
Yeah.
That I was like, hadn't thought of in terms of like latent causes before.
Amazing.
But it's super interesting.
Yeah.
Yeah, it's cool. Thank you.
Thank you. We love each other.
Is it okay if I ask one more question?
No, it's not okay.
Thank you all of you. She's coming to your lab soon, so
it's already